Okay, this is a lump of lead. It's a metal, therefore it has metallic bonding, and it's a giant structure, so it's a giant metallic lattice structure. Giant structures have relatively high melting points and boiling points. The melting point of lead is not that high, but it's certainly not in the form of a liquid or a gas, as you can see. Doesn't look much like a metal at the moment, but let's just give it a bit of a scratch. There you can see the shiny surface of lead, which of course is characteristic of metals. This is zinc, much harder metal than lead. As you can see, trying to scrape the surface to get anything, just a slight shininess there, but if I turn it over and give an example of a couple of others, now what you can see here is very much the crystalline nature of the zinc metal. It's once again metallic, high melting point and boiling point, strong metallic bonds need to be broken, many strong bonds need to be broken to melt this. It's a lattice structure, and this is demonstrated by the crystalline nature, the repeating pattern that you can so clearly see. Now of course you don't need to take a lump of zinc like this and break it up and just to see the crystalline nature. All that you need to do is to go outside and have a look at some lampposts, for example, that have been galvanized, and you'll be able to see the crystal structures of the zinc there as well. This is sodium. It's still a metallic structure, group bond metal. The bonding, the metallic bonding in sodium is a lot weaker than others. The melting point of sodium is relatively low, but it's still described as metallic bonding, strong metallic bonds holding the lattice, the giant lattice structure together. Let's see if I can demonstrate the softness of it. It's rather squidgy sort of material, so let's see if I can grab it and cut it. There we go, and you can see the shiny surface there. You can see it's a very soft sort of metal because I can very easily just squeeze it with the forceps like that. There we go. So it's a very reactive metal, generally kept under oil to prevent it reacting with the air. This is barium, another metal, group 2, right down at the bottom of group 2. It's again a fairly reactive sort of metal in that it's kept under oil to prevent it reacting with oxygen in the air. And although it looks a kind of bluey white solid, let's see if I can give it a bit of a scrape too. It's much harder than sodium, and trying to get some sort of surface, shiny surface. Very difficult to actually see any shiny surface there. So the metallic bonding in this is much stronger than in sodium, but again it's still metallic bonding, relatively high melting point, lattice structure, although you can't see the crystalline nature in this at all. Just looks very oily. This is graphite. It's a giant covalent structure, macromolecular structure if you like. High melting point. In fact, its melting point is higher than the allotrope of graphite, which is diamond. But unlike diamond, which is very, very hard, graphite is a relatively soft sort of material. You can see I can break off little bits of it very, very easily. And of course, one of the uses of it is as pencil lead. This is white phosphorus, a truly wicked sort of material. I really don't like handling this material at all. It exists as P4 molecules. It's kept underwater to prevent it reacting with oxygen in the air, and if I left it out for any length of time, it would spontaneously burst into flames. Again, simple molecular structure. It's relatively soft, and you may actually see it's beginning to fume already in the air. So I'm going to drop it back into its water very, very quickly, because I hate this stuff. Thank you. Got rid of it. This is red phosphorus. This is an allotrope of P4 white phosphorus, but whereas white phosphorus has a very strained ring tetrahedral structure, this is a polymeric structure, doesn't fume in moist air, but it has exactly the same chemical properties as phosphorus, because it is essentially the same. So this is sulfur. It's a simple molecular structure, but you can see it exists as a lattice. The crystalline nature, the shiny surfaces of the crystals there. It's quite a soft material, very easy to break off bits of the material. Simple molecular structure, S8 molecules, relatively strong covalent bonds within the molecule itself, but weak van der Waals forces between the molecules. Okay, let's have a look at some iodine. Iodine, you can see, is a black material. It has a shiny surface, suggesting that it has a lattice structure, but it's not a giant structure. We're talking about simple molecular compound here. I2 molecules, the strong covalent bonds holding the two iodine atoms together, but the lattice structure itself between the molecules is held together by weak intermolecular forces, weak van der Waals forces. You can really tell that this is not a giant covalent structure, a giant structure with a high melting point, because you can see the effect on the paper is that it's diffusing, the iodine molecules are diffusing into the paper, suggesting that we've got very weak bonds holding the lattice structure together. This is sodium chloride. It's ionic. It's a giant lattice structure, giant ionic bond structure. So you've got strong ionic bonds throughout the lattice structure, so it'll have a high melting point. It's crystalline in nature, so you can see that it's a lattice structure, and it's fairly brittle, which is one of the characteristics of these materials. If I can break it up, there we go. You can see that I can break it along the cleavage planes So it tends to break like that. So this is quartz from Snowdonia. It's silicon dioxide. It's a giant covalent lattice structure this time. High melting point, strong covalent bonds throughout the lattice structure. It's a very hard material, very difficult to actually break anything off. As you can see, very little coming off for that. It's hard, high melting point, but it will, if I smash it, will smash along cleavage planes. You can see I'm not having much luck with that. So this is hexane. It's a simple molecular compound, strong covalent bonds within the molecules, but weak intermolecular forces between them. You can see that it evaporates very quickly indeed. But notice, of course, that we're not breaking those strong covalent bonds within the molecule itself. All that we're doing is disrupting the weak van der Waals forces between them. All gone.